Hello, let's discuss 18.6 in Klein's organic chemistry textbook. So here we want to start talking about reactions at the benzylic position. So if we have an aromatic ring, okay, these hydrogens here are called phenyl hydrogens because they're directly attached to the phenyl ring. But if you have hydrogens that are located, say for example, right adjacent to the benzene ring or the phenyl ring, we call those benzylic hydrogens, okay? So there's many hydrogens in this molecule. I won't draw them all, but these ones right here are called benzylic hydrogens, and this guy right here that I'm dotting is called the benzylic carbon, okay? Now, benzylic hydrogens are quite reactive in radical reactions, and that's because of the resonance stabilization afforded at the benzylic carbon. So you can oxidize benzylic carbons to benzoic acids if you have a benzylic hydrogen present, and that is the requirement, okay? Now there's two ways to do this. There's the Jones reagent. The Jones reagent, as you know, is sodium dichromate, sulfuric acid, H2O. In my class, I just write it Jones. You can look this up if you really need to know all those alphabet letters, okay? So if you have a nice little phenyl ring here attached to a single carbon atom, for example, and you treat this with Jones reagent, this oxidizes all the way up to the carboxylic acid. And I'll just draw the C in there so you can see that it's still there. So this makes the carboxylic acid, okay? Now, if you have more than one carbon present, this also will oxidize to the carboxylic acid, but you'll be wasting a few, okay? So if I show you which bond becomes cleaved, it's this carbon-carbon bond that becomes cleaved in the reaction. So if we treat this with the Jones reagent, we'll make the benzoic acid. And you're essentially throwing away the other three. That's going to form a carboxylic acid. Okay. Normally we're focused on the aromatic chemistry here, so we would draw this as the major product there. Now, if you have two carbons, the single carbon becomes CO2. So if you have something like this, and we treat this with the Jones reagent, we'll form benzoic acid. And, carbon dioxide gas, okay? So that's where that carbon right here goes. And once again, we're basically breaking a carbon-carbon bond. So for atom efficiency, normally we do this reaction in green. We take something with just a methyl group like toluene and oxidize it with the Jones reagent to form the carboxylic acid. Now, the thing you need to memorize here is that it requires a benzylic hydrogen. All right, and I'll draw that in here. I'll just draw one of the H's here, I'll draw one of the H's here, and I'll draw one of the H's here, okay? So don't memorize just the fact that you have a carbon there and that's what's changing. So if we have something like this, okay, and we treat this with a Jones reagent, okay, we will form the benzoic acid on the left position because we have benzylic hydrogens on that carbon, but the tert butyl group does not have any benzylic hydrogens, so it remains unreacted, okay? So if I may, I'll draw those hydrogens in with green, and so those three hydrogens are benzylic hydrogens, and that allows this reaction to work. Now, if you have a molecule that has two carbons, all right, you're going to oxidize both of them, okay? So if we have a Jones reagent here, this is generally used in excess anyway, this will form benzene 1,2-dicarboxylic acid, okay? So we'll form a carboxylic acid at the 1 position, a carboxylic acid at the 2 position. Okay, so that's a dioic acid. Now another reagent that can be used for this chemical reaction is potassium permanganate. You technically add potassium permanganate, water, and you heat it up. This might be boiling reflux for like 12, 18 hours overnight or something. And then you go in, you add acid in the second step. But I'm just loose with the memorization of things in my class at least. So just write KMNO4 above the arrow and that will be sufficient, okay? So if we have something like this guy here, okay, we'll put a chlorine over here, we'll put a methyl going up, and we treat this with potassium permanganate. Okay, we'll form orthochlorobenzoic acid. Okay. So we're modifying that benzylic position. We're oxidizing it from just a methyl group or an ethyl or something like that, all the way up to the carboxylic acid. So that's quite, useful. All right. Let's do some practice problems here. Well, that's the conceptual. Problem 1819 in the book. Draw the expected product when each of the following compounds is treated with chromic acid. So we've got toluene. Toluene is the common name for methylbenzene. And if I treat this with chromic acid, this will form benzoic acid. Okay. So above the arrow, I'm just going to write Jones so we can see what that entails. In B, we have meta-ethyltoluene, and we'll go ahead and see what happens here. As I mentioned, if you have 2 carbons and they both have benzylic hydrogens, they're both going to be oxidized to the carboxylic acid. So this will make meta-benzene dicarboxylic acid. And like I mentioned before, we ignore that extra carbon atom, which changes into carbon dioxide probably during the reaction conditions. In part C, we have a much more complicated looking molecule. And if you encounter something like this and you're just beginning, it's a good idea just to draw in the benzylic hydrogens. So this guy here, remember carbon has 4 bonds to it. So we need to sketch in the hydrogens, and the tert-butyl group has none. So we want to oxidize those carbon atoms that are benzylic and have these green benzylic hydrogens. So if we treat this with a Jones reagent, we're going to get a molecule that has a tert-butyl group because that guy is unreactive. And then we'll have a carboxylic acid at this position here. Okay. And another carboxylic acid at this position here. Okay. I won't try to name these, and we'll just call it quits for there, okay? Now, another reaction you can do with benzylic hydrogens or benzylic positions of an aromatic ring is to do a radical bromination using NBS. So if you have, for example, toluene, okay, and you treat this with N-bromosuccinimide and heat or light. Light is abbreviated HNU, HV it looks like. What you'll form here is something called benzyl bromide. Okay, and what you're effectively doing is substituting one of these hydrogens for a bromine, and that's called a radical halogenation or a radical bromination reaction. Okay. And it's a free radical bromination, and it's at the benzylic position. I'll just write C bond to H. So you need a benzylic hydrogen for this to work, of course. So if you have a more complicated molecule, okay, the very selective hydrogen that you're going to pull off to make the benzylic radical is that hydrogen there. So if we treat this with NBS and light, we should get the benzylic halide, or the benzylic bromide product, where the bromine is now attached at that benzylic position. So it's very selective for the benzylic position. This comes from the radical halogenation chapter. I don't remember the chapter number, where you treat allylic substrates with NBS and light, and it selectively brominates the allylic position. Okay. Now, the other thing you can do with allylic halides is treat them with different nucleophiles. So if we treat this with methanol, this will make our ether, and this reaction happens by SN1. Now we know that because this is a tertiary substrate. That is to say, that carbon that I've highlighted is bonded to 3 other carbon atoms. But what I really want to point out here is that this is a benzylic halide. Benzylic halides are particularly reactive because they can become resonance stabilized when you form the carbocation. So let's go ahead and show the curved arrow reaction mechanism for this. The halogen leaves in the rate limiting step, and what you form is a benzylic carbocation. So a carbocation has an empty p orbital, and adjacent to that in the ring is this phenyl ring that has all these p orbitals, right? So this carbocation is conjugated, and we can draw some curved arrows. Let me use the yellow pen for my movement of arrows. We can draw a whole bunch of resonance structures for this molecule. And we're going to see a whole bunch of resonance in this chapter. So it's a good idea to just push through this, copy this down, you know, do it a couple days just to get familiar with this. And what you'll notice is that the positive charge gets positioned at the ortho position here. And then in this third structure that I'm drawing right now, the positive charge becomes in the para position. Okay, so it kind of alternates, okay? And then if we draw another resonance structure, we can position the positive charge at the other ortho carbon. Oops. Okay, and we'll move the arrows once again. Okay, and now we're positioning the positive charge back out on that benzylic carbon. And if you look at where the position of the double bonds are, they've moved over compared to the original structure. Okay. In general, the more resonance structures you can draw for a carbocation, the more stable it's going to be. So this is an extremely stable carbocation compared to just a boring old regular tertiary carbocation, okay? Because of resonance, it stabilizes this positive charge extremely, okay? You can think of it as a hot potato. A carbon with only 6 bonds of positive charge is very reactive, and it's very hot. It's not enjoying its electron density. But if it can share the burden among 2 or 3 or 4 different carbons, then it doesn't seem as bad. Now what happens here is that methanol needs to attack one of these carbons. So I'll just pick this last one here on the bottom of the page since it's accessible, at least in terms of writing. Okay. And we're going to take our lone pairs, right, which is our nucleophile, and that's going to attack the positive charge here on the benzylic carbon. Now, we don't want to attack any of the other positive carbocations that are drawn on this page because we want to maintain the aromatic ring. Remember, aromatic rings are extremely stable, so we want to attack just the benzylic carbon, and in the result of that, we're going to be left with a benzene ring, okay, or an aromatic phenyl ring. So this step here will give us the substituted product. And there I have almost the product, and now methanol, which is in solution, is going to have to deprotonate that to give me the final molecule. Okay. So that's going to give me this after the deprotonation step. Okay, so the first step is going to be the elimination step. Okay. From the starting material to all of these resonance stabilized carbocations, that's the elimination step. This step here, we have methanol as our nucleophile attacking, and then this last step, we have deprotonation. So it's just an SN1 reaction, it's EAD for short, okay? Now the other thing benzylic bromides can do quite readily is do SN2 reactions. So if I've got something like this, benzyl bromide, I can treat this with sodium ethoxide, for example, and that will give me the ethyl ester. Okay, let's name this so we're familiar with the benzyl group here. This right here is called benzyl. So the name of this is benzyl ethyl ether. Okay. All right, so that's a benzyl group. Now, the reaction is just going to occur by an SN2 reaction mechanism, and it's a one-step deal. So you have ethoxide, which has a negative formal charge on the oxygen. So this is our nucleophile. This is going to attack the carbon and kick off the leaving group in one step. Okay, so that's the mechanism. A for attack, all right? All right, the other thing that you can do with alcohols is do various elimination reactions. So if we've got something like this, and we treat this with acid and heat, we can get an E1 reaction occurring to give us a molecule that looks like this. Now, remember, we call this thing styrene. And polystyrene is a polymer made from that. It's used in packing peanuts or the plastic little straws that you use for stirring your sugar or cream into your coffee. So that right there, remember again, is an elimination reaction. You're basically eliminating water from your starting material, and so we'll draw it over here as a product. Okay, I won't go over the mechanism there, but you can guess that you're going to protonate the alcohol because we have acid involved, and you can guess that water is going to be the leaving group to give you that super stable benzylic carbocation, and then that can go on to lose a proton to give you the alkene. Okay, so we've learned quite a few reactions here. We've learned how you can take benzene with a simple alkyl substituent, and we can treat this with NBS and light, for example, to give benzylic halides. Okay, and then we've learned how this can do substitution reactions. I'll just choose a different one, sodium cyanide here, to give benzyl nitrile. Okay, now we've also learned how we can oxidize, say for example with potassium permanganate, to give benzoic acids. Okay, so all these simple reactions should be placed on flashcards and memorized, and we'll start stitching together more elaborate syntheses right now. Okay, so let's look at problem 1820. Okay, in problem 1820, we're asked to propose an efficient synthesis for the following molecules. Now what you want to do is always count the carbons, okay? So off the ring is 6 carbons. We don't need to count those. There's 1, 2, 3, and this has 1, 2, 3. We're just sticking an alcohol at that benzylic carbon. So remember again, you can't really do much with an aromatic that doesn't have any handles or functional groups. So we're going to take this guy here, which has a benzylic hydrogen. I'll draw it in there. And we're going to add NBS, okay? This time around I'll choose heat instead of light. And we're going to form benzylic bromide, okay? I'll draw that change in yellow here. And then we can just treat this with water, neutral water, and that's going to create the alcohol and HBr that comes off of that, okay? Don't use sodium hydroxide. Sodium hydroxide is going to give you primarily the elimination product, I would suspect. So use neutral water. That's your best chance here to create your benzyl alcohol. Okay? In molecule B, we again count the carbons. There's 2, there's 2. So that seems reasonable. We're not creating any carbon-carbon bonds. So what we probably want to do is create a handle out there on our benzylic carbon. So we'll do NBS and heat, okay? And this will transform the benzylic hydrogen to the benzylic halogen, right, the bromide. And then we can treat this with sodium hydroxide. We could treat it with sodium ethoxide or even sodium tert butoxide, you know, to really get only the elimination product. So I'll use sodium ethoxide here. Okay, and that will give me styrene, okay, styrene. In molecule C here, you can see that there's an additional carbon. There's an additional carbon from that weird thing that looks like a C triple bond N. But this right here is cyanide. We sometimes just abbreviate it CN, and that comes from sodium cyanide, NaCN, the reagent. So in this reaction, I would take my toluene starting material. I would treat this with NBS and heat, and that would give me benzyl bromide. Once you have benzyl bromide, I'll use the yellow here to highlight the changes in the functional group once again. So here's a benzylic hydrogen. I'm changing that to a benzylic bromide. And then I can treat this with sodium cyanide as you saw before with my example. And that will give me the benzyl cyanide, or benzyl cyanide, I think they call it. And I'll draw that in yellow once again. Okay, so you can see how sometimes we do addition reactions, sometimes we do substitution reactions. So far we're substituting hydrogen for bromine and then bromine for something else, okay? So let's look at this molecule here. Okay, it looks very scary. All right, there's a lot of carbons here, but look at what's changing. This carbon right here is the benzylic carbon, so we can brominate that position and we can substitute that position. We want to substitute that position for O-methyl, okay? That's OMe, and that comes from sodium methoxide, for example. So in part D, we have this nice six-membered ring here, and fortunately it has a benzylic hydrogen here. And we'll treat this with NBS, so this is part D, NBS and heat, and that will give me the benzylic halide. It's just a larger molecule, but it's still fine. Okay, I think the authors kind of want you to start thinking bigger, but be able to focus in on the smaller parts. Now what we're going to do is treat this with not sodium methoxide. Sodium methoxide is a strong base, and that's going to perform elimination reactions, E2 or E1. We probably want to do, we want substitution, so to favor that, we're going to choose maybe methanol, okay? It's going to reduce the amount of elimination. So we're going to add methanol. and that's going to give us, along with lots of side products here, the desired product. Okay. So you can see the pattern there. We have a benzylic hydrogen. We treat it with NBS in light or heat, and that changes it to a benzylic halide. And then we treat it with some other nucleophile. It could be a strong nucleophile or a weak nucleophile, and then that does substitution to give us the substituted products. Okay. In part B, we treat it with a base, and that eliminates HBr to give us an alkene. Okay. Let's continue working on some more problems. Okay. In problem 1821, this is more challenging because we have one carbon right here, and then we're adding a carbon, a new carbon, okay? So what I think you should do for this problem is, first of all, create a handle. You might think, there's like 3 or 4 different ways to do this problem, but make a handle. Create a heteroatom on there, right? So NBS in light works great. We'll just use that. So take your toluene, treat it with NBS and light, okay? And this is going to form benzyl bromide, okay? Now we want to think about how do we create a carbon-carbon bond from a halogen. One way to do that is to treat this with magnesium in ether to make the Grignard reagent. And then we know that we can treat Grignards with ketones and aldehydes to create a carbon-carbon bond. The only aldehyde or ketone I know of that has only one carbon is called formaldehyde. And so if we treat that with formaldehyde, which is this structure of a ketone or an aldehyde, if you will, and then followed by H3O plus or water, okay, weak acid, this will form phenethyl alcohol, I think they call it, okay? So you might review that step. We've seen that before in the reaction of ketones and aldehydes with Grignards, okay? So review that. Okay, it's a carbon-carbon bond forming reaction, and you need to be very familiar with those reactions at this point in the course. Now that we have this alcohol here, we can think about creating an alkene. So what I think I'll do is make that a good leaving group. Probably just acid and heat will do it at this point, but you could treat this with PBr3, for example, and that will make a halogen, and then you can treat this with a base of some sort to dehydrohalogenate it. So you can treat this with sodium methoxide or something like that. I would predict significant amounts of substitution there, so probably there's a better way. You might, look over this and study it and think of the alternative ways that you could make this product, okay? Okay. So I'm not giving you the best answer here on this YouTube video. I'm just showing you one possible way that, reviews some of the reactions we've seen before in the past. Now, this right here is going to create lots of SN2 side product. So it's not the best choice. There are other ways you could do this, and I'm thinking in my mind of a better way already, okay? So there's the ethyl S ether, okay? Let's do problem 1821. Okay, problem 1822. Starting with isopropyl benzene, propose a synthesis for acetophenone. Hint, make sure to count the number of carbon atoms in the starting material and the product. Ooh. So yeah, there's 3 carbons here, and there's only 2 carbons there. So what do? We need to throw away this carbon here. Now, what I want to think about is the easiest way to make a ketone by throwing away a carbon, and that's going to be ozonolysis. Okay. Thinking backwards, this ketone right here, which is called acetophenone, could come from an ozonolysis reaction that's performed on an alkene. Now you might be thinking, wait a minute, benzene has alkenes or carbon-carbon double bonds, but remember, because of the aromatic stabilization there, ozone is not going to react directly with those carbons of the aromatic ring. So we now need to think about how can we make that alkene, and we've seen an example of this already with styrene. So what I want to do now for the answer is take my isopropyl benzene, treat it with NBS N light, okay, and that's going to transform the benzylic hydrogen to the benzylic bromide. Now this is a pretty whoops, I meant to write BR. Now this is a pretty hindered alkyl halide, so we could treat this with sodium, potassium tert-butoxide or something like that, and that's going to give us the elimination product. There's only one. It's symmetrical in the sense that elimination is only going to give us one product. So I'll use KOTBU here, and that will give me an alkene. All right, methylstyrene, and then what we do is treat this with ozone. It's a two-step procedure. Dimethyl sulfide or zinc and acid is used. I think this book uses dimethyl sulfide. Okay, so the key to doing this problem is outlined here in purple. You should have your ozonolysis reactions that we learned way back in chapter 8 or 9, I believe. And so remember that these bonds can be cleaved and you can create a carbonyl. You can create an aldehyde or a ketone from an alkene. Okay, let's do problem 23. Here's problem 1823. And I love this book because at the end of some difficult problems, they always say, try problems. And then they list 1847, 1857, something like that. And so this is your opportunity to practice even more problems, okay? So here we go. We have this molecule here, and we need to obviously count the carbons. So there's 2 here, and then we're adding 2 more, okay? We're adding 2 carbons. And these 2 carbons are being added way out here, not at the benzylic carbon, but adjacent to it. So what we want to think about doing is how do we make carbon-carbon bonds? One way to do that is from an alkyne. So if we have an alkyne, for example, and we treat this with a strong base, butyllithium, for example, this will create, what does the book use? Sodium amide, I think. So we should probably stick with the reactions that you're memorizing. So sodium amide gives you an acetylide, and then remember that we can alkylate that. So if we added this to a primary alkyl bromide, for example, we could snap on 2 additional carbon atoms to that alkyne. Or 3 or 4 or 5 carbons, okay? So we want 2 carbons. That's going to be those 2 carbons there from my ethyl bromide group, okay? And then in yellow here, I've got my acetylene, right? And I need to somehow convert that to an acetylene. So now the problem is going to become, how do I make this guy here phenylacetylene? So let's first brominate this. Okay, this will be a benzylic radical, free radical halogenation reaction. We'll treat this with potassium tert-butoxide, right? That will give me styrene. So I'm almost there. If I treat this with bromine, I'll form the vicinal dibromide. And then if I treat that with excess sodium amide and then water, I'll form phenylacetylene. I'll draw it in green because that matches kind of what I have up on the top of the slide here. Okay, now you might be wondering, how did I know that? Well, I've memorized these reactions. They were flashcards back when I was a student, and then I incorporated and used them in many different synthesis reactions. I haven't seen this problem before. I mean, I guess I've taught this class before several times, but I just don't remember it. So I'm just kind of thinking on the fly here. I remember the reactions, so that's why I'm recalling them quite readily. The hard part is stitching them all together, kind of seeing the pattern. But what I figured out in green here is how to make a carbon-carbon bond. Okay, those are the reactions you definitely need to memorize. Okay, how do you make additional carbon-carbon bonds? And so we're just going to follow the template here that I've proposed in green. We add sodium amide. This makes the acetylide ion. And we know those are good nucleophiles. There's a sodium counterion here. We don't usually draw that, but I'll draw it here. And then instead of just adding RBr, we want to add ethyl bromide. Okay, and that gets me to the that. Okay, so it's pretty tricky. Okay, at that point. Now, how do I go from, this is a lot of reactions, okay? This is already 1, 2, 3, 4, 5, 6. There might be a shorter way, and if you find it and you locate it, great. Let me just think in my mind. 1, 2, 3, 4. Yeah, I can do it in 4 reactions. It's a shorter way. So this is kind of pedestrian. It's a really long way to get there, but we'll get there with correct reactions. I like doing reactions sometimes the long way. So, 7, 8 steps instead of the 3 that are most obvious, because it reviews more reactions. So here we are, and we have an alkyne. So how do we go from an alkyne to an alcohol? Well, there's no way to do that, but there is a way to go from an alkene to an alcohol. So let me go to the next page here. If I take my alkyne and I treat this with hydrogen and say Lindlar's catalyst, okay? Remember how hydrogenation of aromatic rings is very difficult, so it's not going to happen. But this will make a cis alkene as shown here. Now I want to add water to this, okay? I want to add OH here, and I want to add H here. And you might be thinking, well, the one on the left is secondary, and the carbon on the right is secondary. Good luck with that. But actually, the one on the left is benzylic, and the carbocation there is going to allow water to add to this extremely selectively to give the desired alcohol at the benzylic carbon. Okay? Now, there's a way to do it in, let me draw the right, 1, 2, 3, 4, 1, 2, 3. There's a way to do it in much fewer steps, but I just thought I would show you a lengthy way, okay? Because I didn't see that answer. This is the answer I saw first, so that's what I'm writing down. And all the reactions are correct, Markovnikov addition and all this, okay? All right, that's section 18.6. I urge you to try those additional problems. Do as many synthesis problems as you can. Make sure you work through your flashcards every day. And that's my recommendation and tutoring tip for the day. Thanks for watching.